the Transitional AI Research Group seminar series. This week, our topic is evaluation of LLMs for mathematical problem solving. And this seminar presentation is part of a master's group research project, which happened last trimester under my supervision. And that came about from a discussion in our school about the importance of LLMs in the education system and the role, how critical it is. And we had DeepSeek being released then. So that was a bit of an issue back then. So we thought that rather than just talking about it, let's just work it out, check how good a DeepSeek actually is, and just not on benchmark problems, but some problems even from our school. So here it is. So I introduce you the team. We have Ruanan Wang, Runshi Wang, Cheng Feng Wu, Kingling Zhou, Yuan Shen, and me. And these are all that we are all the co-authors of the paper, and Ronan will lead this seminar presentation. Thank you, Ronan.
Welcome to our seminar today. Our seminar topic is evaluation of LLMs for mathematical problem solving. This seminar will divide into 6 parts. So let me introduce the first part, introduction. In recent years, with the appearance of big data and artificial intelligence, large language models such as GPT, DeepSeek, and Gemini have had a wide impact in various fields. We have also noticed that they are gradually entering the field of education, especially showing unique potential in mathematics learning. As we all know, mathematics is a basic subject that requires logic and abstract thinking. It is widely used in fields such as finance and engineering and so on. However, in traditional learning, many students only stay at the level of memorizing formulas and theorems. They can't apply knowledge flexibly. Um, so after a long time, they will lose the initiative to learn. uh, the advancement of educational technology are changing this situation. Online platforms offer many resources and exercise for students. They can learn anytime and anywhere. And the addition of AI tools opens up the possibility of personalized teaching. In particular, the LLM through a natural language communication training can assist the students understanding complex concepts and provide some ideas for students. Based on this background, we want to evaluate the performance of current mainstream LLMs for math problem solving. We choose 3 models, GPT-4, DeepSeek V3, and Gemini 2, to test them on 3 major data sets: JSMK, Math 500, and UNSW problem sets. We also decide automated scoring structure to comprehensively evaluate the capability of LMs. So next, let's my partner Yuwen to introduce the second part.
Hello, everyone. Math has always been one of the most difficult subjects to teach and learn, especially because of abstract logic and the need of clear step-by-step reasoning. Traditional teaching methods usually do not provide enough personalized support and students may struggle silently without understanding why a solution works. With the rise of large language models like GPT-4, Gemini 2, and DeepSeek, we now have tools that can generate not just answers, but also explanations. These models can walk through a solution, highlight key variables, and adjust their language to fit the learner's level. That is a big opportunity for education. But current research still evaluates models based on one thing, the final answer. That's not enough. It doesn't tell us whether the model skipped steps, misunderstood the problem, or produced logic that is useful in the classroom. There's very little work that breaks reasoning down or leads to additional value. That is where our study comes in. We use a framework called scoring chain of thought that scores a model's solution process across 5 dimensions. That is step completeness, intermediate calculation accuracy, logical validity, problem understanding, and final answer correctness. This let us see not just what the model gets right, but how it reasons. In the next part, Qingling will show exactly how we apply this.
I will present the methodology. We selected three datasets, GSM-8K, Math 500, and UNSW graduate problems. GSM-8K includes simple math problems for primary and middle school students. Problems usually need basic calculations. It checks if models can understand basic mathematical language and reasoning. Math 500 includes harder academic problems, divided into 5 difficulty levels and 7 subjects. Problems usually need multi-step thinking. It checks if models can solve middle to advanced academic math and also compares models' abilities across different subjects. UNSW problems are real graduate level assignments and exams. We selected 3 courses: statistical inference, optimization, and computational methods for finance. It checks if models can explain their reasoning and write full logical proofs. Our evaluation framework has 4 stages. First, for problem definition, we used exam match for GSM-8K and Math 500. EM checks if the final answer is correct. For UNSW problems, we used SCoT, scoring chain of thought. It scores COT and checks if the reasoning steps are complete, correct, and logical. Second, for dataset pre-processing, we clean the data and make sure model outputs match the format of the answers. We also classify problems by subject and difficulty. Third, for model invocation, we called 3 models to solve the problems. Last, for results evaluation, we used automatic EM scoring for GSM-8K and Math 500. For UNSW problems, we used DeepSeek Referee for initial scoring and then manually reviewed and adjusted the scores based on reasoning quality. Next, please. This diagram shows the evaluation workflow. First, we load 2 types of datasets, GSM-8K and Math 500 in JSON lines. and UNSW problems in CSV. Then we clean the data and call each model through the API. Last please. Through the prompt, we ask the model to play the role of a statistic master student. It helps guide the model to answer in a formal and academic way. For GSM 8K and Math 500, we asked the model to return only the final answer. For UNSW problems, we asked the model to return the step, description, expression, and value for each step. We used different evaluation standards for different datasets. For GSM 8K and Math 500, we calculate the overall final answer accuracy. If the model's final answer exactly matches, it is correct, otherwise wrong. For UNSW problems, we score from 1 to 5. 1 means completely wrong. 2 means weak understanding and many mistakes. 3 means the main method is right but has some mistakes. 4 means mostly correct. 5 means fully correct. This scoring allows us to capture both final results and reasoning quality. In summary, our methodology provides a clear and structured evaluation across different datasets. Renxi will present the last part.
Okay, I will introduce the core findings of our study. We evaluated 3 leading large language models, DeepSeek, Gemini, and ChatGPT, as said before, across 3 data sets, GSM 8K for elementary mathematics, Math 500 for advanced mathematical reasoning, and UNSW for practical problem solving. Our goal was to systematically analyze their strengths and weakness in mathematical tasks. These are some sample problems, correct answer, and the large language model answers. And let's start with GSM-8K. Despite GSM-8K containing relatively simple grade school level problems, oh yeah, this page, problems, all models performed at only around 54% accuracy. For example, consider a problem shown in sample. Both Gemini and ChatGPT arrived at correct solution, but their outputs were often verbose or inconsistent in mathematical notation. In contrast, DeepSeek failed to include key intermediate steps, leading to an incorrect answer. A critical issue we identify is that many errors stemmed from misinterpreting problems, conditions, or skipping logical steps. Problems that required combining arithmetic with reasoning, such as adjusting totals after deductions, frequently led to failure across all models. Even at this basic level, large language models reveal a flaw in how they integrate reasoning with computation. Next, move to Math 500, which is designed to assess advanced mathematical ability. We observed a steep performance gradient. Next page, please. Gemini performed well on level 1 problem with 79% accuracy, but dropped to 35% at level 5. Similarly, both ChatGPT and DeepSeek fail from around 60% accuracy at level 1 to roughly 25% at the highest level. This suggests that while models may succeed on simpler tasks, possibly through pattern matching, they struggle to scale to more abstract multi-step reasoning problems. In terms of subject breakdown, next page, please. Pre-algebra and geometry yield higher accuracy, while number theory and intermediate algebra were significant pinpoints, with accuracy dropping to 25 and 38%. A recurring problem was the incorrect application of theorems or improper derivation of properties, especially in number theory. And as shown in graph in last page, the performance gap across difficulty levels widened dramatically, highlighting a practical scalability challenge. And in UNSW dataset, which focuses on practical mathematical problems, ChatGPT achieved the highest number of perfect scores, particularly in optimization problems, where it reached 53%. However, 39% of its errors were due to insufficient justification or explanation. Next page, please. Gemini did well in finance-related tasks, but tended to be verbose, leading to understanding issues. DeepSeek shows the instability, scoring higher in some domains, but failing to generalize consistently across topics. And next. Across all three models, a substantial portion of errors from 20 to 39% involved omitted reasoning or missing explanation steps, as shown in the table. For example, in problems involving Hessian matrix, models often skipped eigenvalues analysis, which is an essential component for complete and correct solution. These results underscore key trade-offs. ChatGPT demonstrates structural familiarity. Gemini shows strength in computational rigor. And DeepSeek reveals capabilities but lacks consistency. Next, looking across all three datasets, we observe some consistent patterns. Gemini led in GSM 8K and Math 500, and ChatGPT performed best in UNSW practical problems. DeepSeek was the most inconsistent but showed clear potential in specialized tasks. And next page. In summary, while large language models demonstrate strong baseline capabilities in elementary and structured math problems, their performance declines sharply with increased complexity. To achieve higher mathematical proficiency, future models must improve in logical consistency, precision in notation, and multi-step intermediate reasoning, especially in complex or less structured domains. This reinforces the need for architectural advance in reasoning, rather than relying solely on larger training data sets. It's also worth noting that DeepSeek is gradually narrowing the gap with leading models. And this is the result part, and go to next part.
Well, how can I control this screen? Well, you can't control it. So should I share my screen or?
You can share your screen.
All right. I can't. All right. Okay. Okay. Let me continue the final part of our presentation, discussion, and conclusion. Well, in our previous research, we used SCoT-based evaluation to gather results. The reasons we use SCoT are as follows. It can avoid a single evaluative criterion of the model's performance in determining the degree of accurate answer, and it can be used to elucidate the fallacies that are inherent in the argument chain of the model. And then, through this process, teachers and designers can comprehend the inequalities in the abilities of the model. And so, okay, and then next page. It's the SCoT criterion. It has been mentioned before, so we skip it. Okay, it is the effect of prompt design on large language model responses. As shown in the table, we can see that different prompt type shows different outcomes. And as the language is more precise and more logical, the outcome will be better. And the statement shows that. Okay, so next one. Okay, so in our previous research, we find that different language models can be used in different educational use. For example, GPT can be used in automatic question and answer and one-step feedback, and Gemini can be used in process-oriented guide questions, and DeepSeek can be used in guide in conceptual and definitional tasks. All right, and however, there are many still limitations, and we have some future work. For example, the limitations includes the evaluation was just based on a small sample from the UNSW question bank. So in the future, we will have more basic numbers, and SCoT relies entirely on manual operations and is difficult to apply directly in larger scale evaluations. So we will explore more comparative effective of different prompt design strategies. And we will also combine human feedback mechanism for fine-tuning. All right, and so in summary, no, all right, so basic arithmetics and word problems are simple tasks for these three language models. But unlike previous related papers, our group has made some progress mainly in DeepSeek. And DeepSeek is capable of answering some structural problems such like linear problems and optimization. When the level of difficulty increases, Gemini will be a better choice, especially in mixture of logic and intermediate calculation. For example, geometric and discrete math. And for higher level advanced problems, uh, such like it is very difficult, like graduated and postgraduate math problems, GPT will be the best choice because it has the standard solutions and the rigorous and reasonable SCoT. So it's our old code and data size. They are all available, and that's all. Thanks. Okay.
Thanks, everyone, for a wonderful presentation. Could you please walk a bit through the code structure, the GitHub repository before we go into questions?
Can I ask a question, Rhoda, when you're looking at this?
It will end in a few minutes, Donna.
Okay.
Right. Continue, please.
Please present in GitHub. Show it folders.
Right. You can continue.
We submit some files in GitHub repo, and we divide them into three parts, and the code and the data sets and the result. And the code is how we go through, how we use our evaluation framework, and we upload the data sets in them and evaluate them, and let let the large models give the results automatically, and the data size is where it is all three data sets we collect from somewhere else, and that's a different formats of data sets. And about the result is the mean result containing large models answers and problems or answers, and some comments and evaluation are they are all stored in CSV file, and actually codes in three files like DeepSeek and Gemini and GPT, we do the same thing, but use different models actually. So the codes thing they are very similar. We just store them in different Python file. Actually, that's an introduction of the GitHub repo.
Okay, thank you everybody for a wonderful presentation. Now we can ask, we can get questions from the floor or questions online. Anybody has a question?
I have a question. You know, like when we
Thank
solve
you.
a problem, right? The way you prompt, right? The way you prompt a question, like for example, you said one of them didn't go into analysis in terms of eigenvalues, right? But if you prompt differently, since suppose that you know what the answer, how to get the answer, right? And you say you follow the guidelines as a solution. Do you think you get better results? Because it seems to me like more of a prompt issue. What you're asking them to do is causing some issues rather than sort of, logically you're thinking, okay, I'm sort of knowing, say if I want to use this as a tool for teaching, right? And you say, well, I want the students to do certain steps, and you give them this prompt, you tell them the steps, would you get a better result? Because it seems like you're only getting less than 60% success rate in all of them, correct?
Yeah.
So do you think that maybe it's your prompt, the way you ask the question, that's getting you the bad results?
Actually, we use the same prompt words for three models. So in the same case, we evaluate them. So maybe the results we control our values, like you say the prompts, and in this case, we just evaluate in a certain case, but not all the cases. Well, as you know, large language models may generate different or different answers if you ask differently, but we ask the same proper word.
Perhaps because the first goal, Donna, was to compare the large language models, so the set of prompts was same. I think you have a valid question that if you are going to improve, the way the prompts are done, of course it's going to improve the solutions, but that's probably a direction for future research. I don't think we have done that much of prompt engineering testing in this work.
Because that would make it more assuring, right? Like if I ask the question properly, because usually when even when we do a research question, if we don't ask the question appropriately, we don't get the right answer, right?
And
that's what I'm asking.
And I think that had also a sister project which was about asking LLMs to generate movie reviews based on subtitles and movie scripts, and we tested the prompt engineering in that project. So whereas it is not that detailed tested in this project, but as you can see, if you see the archive of the paper, there's a lot of things already done in this project, which is more than one paper, actually, focus of one paper. It's like two papers.
No, I'm just saying that. Yeah, I'm saying that. But you sort of led the feeling that I thought maybe I can see where you're coming from, but I also thought maybe the prompt, like especially when you come to the higher levels, like the other two data sets, Math 500 and the other one, they were like easy primary high school stuff, right? But when you start getting
Yes.
to the more difficult stuff, you need to ask the prompt more logical prompts, right?
Yeah, but
You know,
if you look at the Math 500, the LLMs did not do as well as we thought they are good. You know.
yeah, I noticed that, but none of them were really that great. They were less than 60%.
Yeah, exactly. So I think your question just leads to a follow-up project where you do better prompt engineering, and also I think one of the major limitations is like a qualitative assessment of the answers, right? Which we
Yes,
didn't really
yes,
do.
yeah.
So we have like automated marking, which is being done at the moment to evaluate the LLMs, but in exams we do have that qualitative analysis of answers which we should have done, and that could be I think a follow-up
That's your
work where
second paper.
you
That's your future paper. Okay, I'm not saying it, but that would be something
yes,
nice to see, right? That's something to
yes,
reassure that we're going in the
this
right
can,
direction.
yes, I think we have done the code and the software that the foundation is laid. So like for more real world questions, and there could be more different types other subjects in mathematics, um, and that could have qualitative assessment and better prompt engineering, and let's see where the LLMs are. But by the time we may do that, it would be probably next year, and we may have some new LLMs around and maybe they are better.
That's true. Great. But it was
All
a
right.
nice talk. I got something out of it. Thank you very much. Thank you.
Thanks, Donna. So anybody has any other question? Any question from the floor there, Amuchi?
The question I got.
Okay, so we don't have a question. I would like to just take a moment to thank the team. I think in 10, 11 weeks, there was a lot of work that was done, and some was directed by me and some was not really directed by me, but the team came up with a number of solutions to the project and some new strategies to solve the problem, and that just shows that teamwork can do things in a shorter amount of time. And thank you very much, and we hope you enjoy reading the paper, and any questions or comments, do feel free to email us and we'll get back to you. Thank you, everybody.
How many is here?